Algebra 2 honor students, this is the start of a new unit. We're on to Unit 5, and this unit is all about simplifying radicals and dealing with radical expressions. We'll eventually solve some radical equations. And then also we're going to introduce this idea of complex numbers, which is brand new for you this year and exciting stuff. So to get started with our discussion of radicals, we'll start with something that I think we're pretty familiar with. And I would say pretty much almost the entire unit here will be notes by hand. And of course, homeworks are in the packet, so you'll definitely want to have some paper available as you're taking notes on these videos each night. So to get started, the square root of 25, we know that's definitely 5, because 5 times 5 is 25. So what about the negative square root of 25? Well, if we take the square root of 25 and got 5, we're going to negate that and get negative 5 as an answer. And finally, if I take the square root of negative 25, the answer is, what times itself is negative 25? Well, the answer is technically nothing, isn't it? It would be a non-real answer. So that will become something we eventually talk about in this unit, is how do we deal with square roots of negatives? That's coming later on. But for now, we're just going to say, you know what? It's not a real number, because nothing times itself will ever give you that negative result in there. So to go to a question that's come up actually a few times in our classes, when do we need the plus or minus, right? The square root of 25 is just 5. It's not plus or minus 5. And here we just got an answer of negative 5 because the negative is already out front for us, but we just have to be cautious that the square root of 25 is not plus or minus 5. So when do we need it? It's really needed when you're solving an equation such as x squared equals 25. If you're solving that equation for x, when you take the square root of both sides, square root, that's when you can consider that it's plus or minus the result on the right side. So here we would get x equals plus or minus 5 as my answers. So it's only that plus or minus when you are solving and take the square root of both sides. Because keep in mind, if I don't do plus or minus there, compared to this situation where maybe I subtract 25 over to the side with x squared. A way to solve this would be by factoring. And when you set each factor equal to 0, you would get x equals negative 5 and x equals positive 5. So we want to make sure that if we're going to solve in this format, which is certainly acceptable, right? Move the 25 over here, square root. When you physically take the square root of both sides, that's when we write plus or minus. So just as a quick aside there, hopefully that's starting to make some sense as far as when do we write plus or minus. It's only really when solving. If the radical's there for us already, do not include plus or minus. So let's then talk about the process for simplifying. So if we're simplifying radicals, just to start, because we're going to build upon that today. And if we're talking about square roots, we want to determine the largest perfect square that divides in evenly. To the number under the radical. And there's multiple approaches to simplifying radicals, so I'm guessing this is a way that you might be familiar with, but there might be other teachers who have done factor trees and other things to simplify radicals. I like to think about, well, what's the biggest perfect square that goes in evenly to the number underneath the radical? And in terms of perfect squares, what are we thinking about here? We're thinking about numbers like 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, which would be like 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. I mean, that's the first 10 perfect squares that we'd want to think about. But we can even go beyond that depending on how large the number is under the radical. Maybe we'd go to 121 and 144 and 169 and 196 and 225. And 256 and 289 and 324. Okay, I can go on for a little while. But let's kind of start with this initial list up to 10 squared. Hopefully that will take care of things for us. And by the way, we're not really that interested in 1. I mean, it's a perfect square, but of course 1 will divide into everything evenly. So you really want to start your list at, does 4 go in, does 9 go in, does 16 go in? And we just have to be careful because, we want to make sure that we pick the largest from this list that divides in to completely simplify. So for example, if I said, let's simplify the square root of 48. I'm looking at this list here and figuring out, well, what's the biggest perfect square that goes in? Well, definitely want to start at the end there. We'd have to at least backtrack to like 3625. Does 16 go into 48? I believe it does, right? And you could check this on the calculator, but yeah, 16 is going to go in 3 times. So when you break this radical apart into 2 radicals that the product of those numbers equals 48, whichever one's the perfect square, I always list first, because the square root of 16 is 4. So therefore, the square root of 48 simplifies to 4 radical 3. What if you didn't recognize that 16 was the biggest perfect square? And you're like, well, hey, I know 4 goes in. How many times does 4 go into 48? The answer is 12 times. So if you had originally started as radical 4 radical 12, you would then have to square root 12 as part of a simplified answer, but it's not fully simplified yet, because then if you look at the number 12 underneath the radical, you want to say, wait, was there anything else that's a perfect square that goes into 12? And it happens to be 4 again. So you can break down 12 to the square root of 4 times the square root of 3. And the square root of 4 is 2. So 2 times 2 is 4 radical 3. And we eventually get that same answer. But clearly, if we can find the largest perfect square that divides in evenly, then that's going to be the best case scenario. Okay, let's do another practice. We'll make the number maybe a little bit larger to get started here. So for example, if I were to figure out for the square root of 216, we want to look at our list up here and think about, hey, what are the perfect squares that might divide in nicely to 216? And you can play around with some of these values here. The largest one in the list is going to wind up actually being 36. And I'm not even necessarily thinking that that's as obvious, but if you were to on your calculator, you might know a special thing in the table that will help you. I'll show you this in class just so that we all have it. But there's definitely things you can do to the table to quickly check on these perfect squares. So if you wind up breaking this down into 36 times 6 is 216, then the final answer in simplest radical form would be 6 radical 6. All right, we're going to do what looks like the same example, but now I'm putting a little 3 out here. And I'm not exactly sure if you're familiar with that notation, but the 3 in this spot, right with our radical symbol here, is indicating that we're taking the cube root, not the square root anymore, but what would be the cube root of 216? Can we simplify that at all? So when you're dealing with cube roots, this list kind of goes out the window. And what we're looking for now is not a list of perfect squares, but a list of perfect cubes. Look at how nice that cube is. Not too bad. Okay, so what's a good list of perfect cubes? Well, 1 cubed is 1, and 2 cubed is 8, and 3 cubed is 27, 4 cubed is 64, 125, 216, 343, 512, 729, and 10 cubes is 1,000. Okay, so we probably won't see much that goes beyond 1,000 in terms of a number underneath the cube root, but you never know. Here's a good list of perfect cubes that we'd want to be familiar with, because this is what we're going to test. Which one of these divide in evenly to 216? And then we'll kind of go from there. Oh, wait, hold on. 216 is in this list. So 216 itself is a perfect cube. The cube root of 216 winds up being 6. Now, what are we thinking about for perfect cubes? It's what times itself 3 times would produce the number underneath this cube root, right? 6 times 6 times 6 is how we get back to 216. So what if I then said, let's simplify the cube root of 128. Okay. What we want to do is we want to look at our list and see which of these numbers divides into 128 evenly. And I guess the first one I would check, if I'm kind of working my way backwards here, I mean, 125 definitely doesn't go into 128 evenly when we divide, but does 64 go into 128? That's kind of the next probably plausible one to check. And 64 does go in nicely to 128. It goes in twice. So if we recognize that right off the bat, we can easily simplify this to become the cube root of 64 times the cube root of 2. And notice how when I break apart a cube root, we have to write that notation in both spots. Okay, and we'll talk about what that spot is called in just a moment. But this would break down to cube root 64 times cube root 2. What is the cube root of 64? Well, this was 1 cubed, 2 cubed, 3 cubed. This is 4. 4 cubed is 64. So the cube root of 64, therefore, is 4. And your final answer would be 4 cube root 2. That is the simplified version of the cube root of 128. So having this list of perfect cubes, I would say you should probably have at least up to here memorized, the first 5 perfect cubes. And remember, we don't even really care about 1 because 1 divides into all of them. But this is a good list to kind of start off with. I mean, recognizing some of these might be useful, but for the most part, knowing these 4 right here are going to be pretty critical to simplify things with cube roots, okay? All right, let's do a little bit more practice here. So we've got the cube root of 375, and we'll also simplify the cube root of 108. Okay. So what I want you to do is, now's a good time to hit pause. See if you can try these with analyzing our list of perfect cubes that we just came up with, and which one of these perfect cubes, and if we have to go out this far, we can. I don't think we'll need it though. Try those 4, what divides in evenly, and see if you can simplify each of those perfect cubes. I'm going to go over what the correct answers are at this point. So when something ends in a 5, it might be a good hint that 125, as long as it's big enough, that's the perfect cube that divides in evenly. And in fact, 375 is the same thing as 125 times 3. So we can break this down to the cube root of 125 times the cube root of 3. And the cube root of 125 is 5. So the final answer is 5 cube root 3. It's kind of tempting to think that the cube root of 3 is a nice number, but nothing times itself 3 times is going to give you 3 as a result. At least not a nice number, is it? All right, cube root of 108. Similarly, if I look at that list and I think about, hey, what goes in nicely to 108? It winds up being 27. And 27 goes in 4 times. So if I break it down to cube root 27 times cube root 4, the cube root of 27 is 3. And the simplified form of the cube root of 108 is 3 times the cube root of 4. It takes a little bit of practice, and it's really common to forget this little cube root as my symbol there. We're so used to writing square root, that we forget sometimes this value, which you'll see in a second, is called the index. Okay, the value of the root that you're taking, but it's important to include because 5 square root 3 is clearly not equal to the cube root of 375. All right, let's talk a little bit more about notation then. So as far as notation goes, if we have something of the form, I would read this as the nth root of k. The number that's right here, I just referred to it a second ago, is called the index. And it's the root that we're taking. So if there's no index written, we're assuming that it's the square root. We don't usually write a 2 there for square root, this radical symbol, without anything written. We operate under the assumption we're taking the square root. But we're going to see a lot of index values that are now maybe a 3 or a 4 or a 5. And that would indicate that we're taking the cube root, the 4th root, or the 5th root of whatever this number is underneath. So the number underneath is known as the radicand. And these are just fancy names for these terms. I don't think we will wind up using them too often. And then this right here is the root symbol. Okay, we're so used to calling it a radical, but radical we typically associate with finding square roots specifically. So that root symbol, according to this index, could be the cube root, the 4th root, the 5th root. Okay, just some quick notation there. All right. When we talk about taking square roots, if you have a perfect square underneath the radical, the square root of k squared winds up equaling k then. So we're going to deal with some variables in a little bit. And one thing that we'll see is that we can actually change back and forth between radical and exponent form. If you're just taking the square root of some value k, that's the same thing as doing k to the 1/2 power. And you can check me on that. I mean, you know what the square root of 64 is, don't you? The square root of 64 should be 8. And what I'm telling you is that 64 raised to the 1/2 power is also 8. Okay, so notationally, these two things, square root, 1/2 exponent, mean the same thing. We can extend that to cube roots as well. The cube root of k cubed, if this is a perfect cube underneath, is just k. And if we just have the cube root of k, that's the same thing as k to the 1/3 power. So we can confirm that pretty quickly too. We can get cube roots on the calculator by hitting the math key right here. So if you hit math, it's option 4 for cube root. The cube root of 27 we know is 3. 27 raised to the 1/3 power is also 3. So those two mean the same. So therefore, in general, if you have the nth root of k to the n, if the index and the power on the inside match, then this just simplifies to k. And the pattern across the bottom row here is that if we're taking the nth root of k, this is the same thing as k to the 1/n power. Those two things mean the same thing. Okay. And now that we've seen a little bit more with cube roots, a quick note here is from our discussion at the beginning today, the square root of something like -64 is a non-real answer, right? Nothing times itself will ever be -64. But what about this now? Cube root of -64. Can you multiply something by itself 3 times to get a negative? Yeah, a negative times a negative times a negative is negative. So you can take cube roots of negatives with no issue at all. The cube root of -64 is -4. Because if the cube root of +64 is 4, the cube root of -64 is -4. All right, let's see how this kind of plays out with some quick solving here. So if I said to solve something like x squared plus 10 equals 74, we can solve that pretty easily, right? The first step might be subtract 10 over to this side, so x squared equals 64. And like we saw at the beginning of the lesson, square root, we get x equals plus or minus 8. When you take the square root of both sides, it has to be plus or minus 8. And we can double check that 8 squared is 64, and parentheses around -8 squared would also be 64. All right, if I gave you something like x cubed plus 27 equals 0, you would subtract 27 over first. And then the only difference is that if I want to get rid of an x to the 3rd power, how do I just isolate x? Well, if you have x cubed underneath to get x, what should I do? I should take the cube root of both sides. So just make sure you're using the appropriate root here. It's the cube root of this side and the cube root of that side. And in the end, we get that x equals the cube root of -27. Be careful here, is only -3. So we have no plus or minus if we're dealing with odd roots. So if it's the cube root, the 5th root, the 7th root, you can take the cube root of a negative and it's just -3. -3 times -3 times -3 is -27. Okay, so be a little bit careful about that, that here you have to do plus or minus. On this side, it's incorrect if you do the plus or minus. Okay. Let's talk about simplifying with variables. So for example, if I have the square root of 81 x to the 4th y squared, and I wanted to simplify that, We can simplify this by taking, well, the square root of 81 is 9, so that's pretty easy for us to do. And then as long as these are even exponents, they would wind up being perfect squares. So the square root of x to the fourth is actually x squared, because x squared times x squared is x to the fourth. The square root of y squared is y, because y times y is y squared. So notice what happened when I took the square root of this. If there's variables underneath, essentially these exponents just get cut in half. And why does that really make sense? Because the square root is the same thing as raising something to the 1/2 power. So that's why those exponents wind up essentially just getting cut in half. If I went over to something maybe a little bit more challenging, like the square root of 27, x to the 6th, y to the 7th, z to the 8th. Not every term underneath this radical here are perfect squares. I mean, here, 81, x to the 4th, y squared, we're all perfect. But we're going to have to break this apart into two radicals, one that's a perfect square and one that's a non-perfect square. Okay. So when we think about 27, that's not so bad. What's the biggest perfect square that goes into 27? It should be 9, because the square root of 9 is 3. So if I take 9 out of this, when I say out of it, it's 27 divided by 9 is 3 left over there, right? These two things have to eventually multiply to the original, which was 27. Okay, in terms of the perfect squares, let's analyze the variables now. X to the 6th, if it's an even exponent, it already is a perfect square, so that can get paired up with the 9. Y to the 7th is not a perfect square, but if you were to separate this into y to the 6th times y, this is the largest group of y's you can take from y to the 7th, such that it's still a perfect square. So I'm going to put y to the 6th with all the perfect squares, and then just one more y over here. Right? Y to the 6th will be nice when I take the square root of it, but you still have a y left over for that total of y to the 7th. And then z to the 8th, well, again, if that's an even exponent, all the z's can go in the perfect square here. So actually, I had a big radical going over here, but I don't have anything else left to put in here. It's just the square root of 3y that's left over. So the last step then is take the square root of that perfect square there to get 3. X will be to the 3rd power, right? We said we're cutting the exponents in half. Y to the 3rd, z to the 4th, times the square root of 3y. That is the simplified form of what we started with here initially. Okay? That definitely takes some time to get used to. So I promise we'll get some more practice with this. In fact, the last thing that I want to do in the lesson is why don't we practice with some cube roots in the mix. So if I said to simplify the cube root with some variables, 125 x to the 9th and y cubed. What's going to be the big difference with cube roots is that we're looking for those exponents not to be able to cut in half anymore, but for a cube root, the exponents get divided by 3. Or you can think of it as times a third, right? Because that exponent, when you take a cube root, is like raising it to the 1/3 power. Well, the cube root of 125 is a nice number. It's 5. Okay, it's a perfect cube. And these are then both going to be perfect cubes. If this is an exponent divisible by 3, then this is going to break down to x cubed times y. Divide those each by 3. This is now y to the 1st, right? And that makes sense. Y times y times y is y cubed. X cubed times itself 3 times would be x to the 9th. So that's the simplification of cube root 125, x to the 9th y cubed. All right, let's try this one. Cube root of -54, x to the 4th, y to the 16th. Okay. So if I were to break this one apart, it's definitely not a perfect cube. So we're going to have two different cube roots that are multiplied here. What's the biggest perfect cube that goes into 54? Think about your list. We have 8, 27. 64 is already too much. 27 is going to go in twice. And since this is negative, I'm going to keep the negative with the 27 and put the 2 over here. Okay, negative 27 times 2 is definitely negative 54. Then what I want you to think about is what's the largest group of 3 x's and the largest group of 3 y's that we're going to wind up taking from here. So in other words, if you were to divide this by 3, what's the remainder that's left over? Okay. Well, you can actually take for this, you can take a full x cubed, and you're left with x to the first over here. And similarly with the y's, what's the largest exponent I can leave over that's still divisible by 3? I can leave y to the 15th over here, because 15 is divisible by 3, but I still then have y to the first in the other cube root. So this is now a perfect cube. The cube root of this would be -3, x to the first, and y to the 5th. That's going to be times the cube root of 2xy. Okay. Like I said, it definitely takes some time to get used to this. Let's do maybe one more, and then we'll do some practice next time I see you in class. What about the 4th root? Okay, so the 4th root of, let's do 32 x to the 4th, y to the 9th. We haven't dealt with any 4th roots yet. And I'll tell you, none of these are a number to the, well, actually, this is perfect, right? This is something to the 4th. But these and this term are nothing to the 4th power. So when I think about things to the 4th power, I mean, 1 to the 4th is 1, which we don't really care about. 2 to the 4th is 16. 3 to the 4th is already very large. It's 81. So when I'm thinking about that list of things to the 4th power, 1 to the 4th, 2 to the 4th, 3 to the 4th, 16 does go into 32. So when I break this apart, 16 goes in twice. So here's going to be the one that perfectly comes out nice. This is going to be the part that's still left under the 4th root. We just discussed that x to the 4th is going to come out nicely if I grab that whole piece of it. But I want to take as many y's as I can out of y to the 9th such that the exponent is divisible by 4. And I'm hoping you're thinking that you can take all the way up to y to the 8th out of that. And we still have one y left over here. So when all is said and done, the 4th root of 16 I just showed you up here is 2, because 2 times 2 times 2 times 2 is 16. The 4th root of x to the 4th is x. Now we're dividing these exponents by 4. Y squared times the 4th root of 2y. This is definitely the one that takes the longest to get used to. So like I said, definitely more practice coming your way when we get to the recap. That's it for today's lesson. We'll catch you next time.